Integration isn't always the easiest thing to do in calculus, but it helps when you have a few tricks up your sleeve. Today I'm going to tell you about the trick of substitution when you're trying to integrate. So be sure to follow along, subscribe, and share the video with somebody you know. When you're using the substitution method for integration, it can be a little tricky. So sometimes it helps starting from the reverse angle, meaning the derivative, right? The derivative is the reverse of integration. So what we're going to do is we're going to take the derivative of this problem and then we're going to integrate and work backwards so you can see exactly how the substitution method works. So the first thing we're going to do with this problem, like I said, is take the derivative. I'm going to rewrite that square root to have our fractional exponent. So we have y equals x cubed plus 5 to the 1/2 power. Now hopefully you see an inside piece here and an exponent, and you're thinking chain rule, chain rule, chain rule. Okay, so substitution method is going to undo the chain rule. So let's go ahead and take the derivative. So y prime would equal derivative of your outside piece. Remember, the outside piece is going to be the exponent. So 1/2 comes out front. You leave your inside piece. Subtract a power, -1/2, times the derivative of your inside piece, which would be 3x squared. So this is the derivative, meaning if this was an integration problem, this is what you would be starting with. So watch what I'm going to do. Let's say we wanted to integrate this. The integral of 1/2 x cubed plus 5x to the -1/2 times 3x squared dx. Remember, you got to have that dx. Here's the thing. We already know the answer. This equation right here is your answer. So now we need to start paying attention. Okay, what does this integral and the answer have in common, and what don't they have? So first of all, what they do have in common, they both have this inside piece. That x cubed plus 5 is there for both of them. Notice that the derivative of the inside piece does not show up in your answer. It has to be in the integral, but it does not show up in your original function answer. Now let's look at the exponents. Notice that what we did here, we took our -1/2. And what's the normal rule when you integrate? You add an exponent. So if you take -1/2 and add 1, we do get +1/2, okay? But what about this guy out front? The 1/2 does not show up in your answer because remember, for the rule for integration, when you add 1 to your exponent, you put 1 over that number out front. These pieces right here will cancel out, and this is how you'll get your answer. So notice that the integration piece looks really messy, but sometimes the answer looks much simpler. So let's break this down. Here is the formal notation that you need to get in your notes. When you integrate the chain rule, this was the chain rule that we took the derivative of. Notice you have the derivative of the outside piece, you leave the inside piece, times the derivative of the inside piece. When this is what you're integrating, notice that your inside piece is what stays the same, and that you integrate your outside piece. And the derivative of the inside piece does not show up at all. And yes, don't forget your plus c. Let's do one more using trig so you can see how this works. Y prime equals derivative of sine, good, cosine, leave your inside piece, times the derivative of your inside piece. So the 1/2 comes down front, the 2 and the 1/2 cancel. You have x to the -1/2 power. Okay, now if this is our answer, this is what we would be integrating to get back to the original. So let's integrate. Cosine of 2x to the 1/2 times x to the negative 1/2 dx. We know that our inside piece will stay the same. The derivative of our inside piece needs to be in our integral, but it will not be in our answer. And then all we do is integrate cosine. What did we take the derivative of to get cosine? Your answer is sine. So let's get this in our notes so you know exactly what you need to be doing for each problem. Put this in your notes. The first thing you need to do is you need to identify your inside piece and its derivative. Step 2, the derivative of the inside piece must exist, but it does not show up in your answer, but it must be there. And you'll see here, I say, if not, use a magic wand. I'm going to tell you all about that in just a minute. Step 3, you're going to integrate your outside piece using normal integration rules. The last step is when you write your answer, you're going to leave your inside piece the same. Let's try some examples. The first thing we have to identify in this problem is what's the inside piece and what's the outside piece. Well, if you know your trig integration, you know that secant tangent was the answer to a derivative. So in this problem, our inside piece is actually the 2x. So does the derivative of our inside piece exist currently? Nope, it doesn't. But can we make it exist? Can we write a fancy looking 1 to make it exist? And here's what I mean. What's the derivative of 2x? It's just 2. 2 times 1/2. Sorry, my drawing is not all that great, but isn't this just a fancy looking 1? Isn't 2 times 1/2 just 1? Right? So watch what I'm going to do. Here's the derivative of my inside piece. I'm going to put my 1/2 out front of the integral. It doesn't matter if it's on the outside or inside the integral. It's just going to come down with your answer. But remember, the derivative of my inside piece will not show up in my answer, but he's got to be there for the chain rule. So my 1/2 comes down. So now we have to integrate our outside piece. Our outside piece was secant x tangent x. So what did we take the derivative of to get secant x tangent x? If you don't remember, get out your trig notes. But it's secant x. So secant, and leave your inside piece the same, plus c. Here's your answer. Now, check yourself. Make sure you have it right. Take the derivative of this and see if you get it right. Let me show you. Rewrite my problem here. I'm going to take the derivative. 1/2 comes down. Derivative of my outside piece is secant tangent times derivative of my inside piece. C, derivative of c is 0. So look what you get. This and this drop, and if you remember, that is what we started with. So what's nice about the derivative and the integrals is you can always check your answer by doing the opposite. Now this one looks pretty scary, but which do you think is going to be your inside piece? I'm going to take the biggest piece here. I'm going to say that this is my inside piece, and I'm going to ask myself, okay, what's the derivative of my inside piece? Derivative of this is 2x plus 2, and the 3 falls off. Now hopefully you're seeing that this kind of looks like that guy, only he needs a 2. So again, we're going to use a fun magic 1 to create that 2 that we need. So I want the 2 here because I want him to distribute to this. So basically, I have the derivative of my inside piece. But I can't just go ahead adding a 2 to every problem. I got to put a 1/2 out front because my 1/2 and my 2 make a 1. All right, now, We found the derivative of our inside piece. Yes? Now we integrate the outside piece. So the outside piece in this problem is our exponent. Let's integrate. We leave the inside piece the same. When you integrate, you add an exponent, and you have 1 over that new exponent out front. But we have this 1/2 that also has to come down here. The derivative of the inside piece does not show up in our answer at all, but we do have to add a plus c. Now you just simplify your answer. Now you have 1 over 32, leave the inside piece, 2x minus 3 to the 16th power plus c. And that's your original y. And again, if you're not sure, take the derivative and check it out. Well, think about this. If you take the derivative of this, the 1 over 32 is going to stay, and guess what? That 16 is going to come out front. You simplify 16 over 32, you're going to get your 1/2. You're going to leave your inside, subtract an exponent, derivative of the inside is going to give you this guy right here. So we're good to go. There always has to be trig problems, right? Because just when you have something down, they have to throw this in your face. So now what I'm going to do here is notice where the exponent is on sine x. I'm going to rewrite it a little bit to make it a little easier to solve. So we're going to have the integral of sine x to the 4th power of cosine x dx. Now you may be asking, why did she do that? Well, because now if you look at the chain rule, the inside piece is sine x. What's the derivative of sine x? Cosine x. The derivative of our inside piece is already there, so we don't need to add anything. Now we just need to integrate the outside piece. So when you integrate the outside piece, you add an exponent and put 1 over that new exponent out front. The derivative of the inside piece goes away, and you leave the inside piece the same. And that's it. That's all you got. Sometimes they're not so scary. You just got to give them a chance. Again, try this one. What's the inside piece? In this problem, the inside piece is 2x. Derivative of your inside piece is 2. He's got to show up, which means we need a 1/2 out front. Okay, so when we integrate this, the 1/2 is going to come down. You're going to integrate your outside piece. That's the sine. What did you take the derivative of to get sine x? And hopefully you're thinking not only cosine x, but negative cosine x, because the derivative of cosine is negative sine x. But I can't just write x here, so I had to fix that. It's 2x, because you leave your inside piece the same. So I integrated my outside piece. I left my inside piece the same. The derivative of my inside piece does not show up in my answer. I just add a plus c here, and I'm good to go. Again, with all of these, if you have any questions, check your work. This is the easiest way for you to know whether or not you got the answer right. And I know people get lazy and you stop doing it. Make sure you got your plus c on there. Check your work to make sure you got the right answer. All right, this one's a little tricky. I'm going to pull apart our secant x, and you'll see why here in a minute. Tan x, secant x times secant x dx. I'm going to put these in 2 groupings like this. And here's why. I can pick which one of those I want to be my inside or my outside piece. What I'm going to do is I'm going to raise this to the 1st power. And I'm going to make my secant x my inside piece. Because what's the derivative of secant x? The derivative of secant x is this guy. So does the derivative of the inside piece exist? Sure does. We don't even have to add anything. Now we just have to integrate the outside piece. So notice I'm using my exponent of a 1 as my outside piece. So when I integrate that, I have to add an exponent, put 1 over that new exponent here. secant squared, derivative of my inside piece drops out, plus c. And this is your answer. This one looks a little uglier, so let's give it a try. First thing I'm going to do is rewrite this so it's not in a fraction, and I'm going to rewrite my square root as a fractional exponent. So we're going to have the integral of 9x squared times 1 minus x cubed to the negative 1/2 power. The negative is what brings that up from the denominator, and the square root is a 1/2. Now I see that my inside piece is going to be this. And first thing I want to do is figure out what is his derivative. His derivative is negative 3x squared. Well, we have part of that, don't we? Check out what I'm going to do with this 9. So watch what I'm going to do with this 9. First of all, I'm going to rewrite this 9 as 3 times 3, and then this x squared comes right down. The only thing I have to address is this negative sign. So I'm going to put a negative here, rewrite this like this, and have a negative inside with that guy. So there I have my derivative of my inside piece. And then this side stays the same, the inside piece stays the same, dx. And now when I integrate, this negative comes down, so does this 3. This is the derivative of my inside piece, so he does not show up in my answer. I leave my inside piece, and then I have to integrate my outside piece, which means I have to add an exponent. So adding 1 to 1/2, negative 1/2 gives me positive 1/2. And then out front here, I have to have 1 over 1/2. Integration rules, plus c. So now we have negative 6, right? Because 1 over 1/2, that guy's going to flip. You're going to have 3 times 2. Leave the inside piece. And here's my answer. All right, let's figure out this inside piece. Derivative of this inside piece is just going to be 7. So again, I'm going to use that trick, and I'm going to pull apart 28. 4 times 7. Here's my inside piece. So now the derivative of my inside piece exists. Doesn't show up on my answer, but he's got to be there. Now I can just integrate the outside piece. The 4 is going to come along for the ride. I leave my inside piece the same. I integrate my outside piece. You add 1 over 4 here, plus c. Hopefully you see, those pieces drop. You're just left with 7x minus 2 to the 4th power plus c. Hopefully this method of substitution gave you another way to look at integral problems, and it made the process easier for you. Please be sure to subscribe, let me know if you have any comments, questions, or topics you want me to cover, and share the video with another calculus student.